Hi, good morning, everybody. I wanted to talk today about 4 topics that I thought were interesting in the DNS operations world that are important for network operators to be up to speed on. The 4 topics are about applications doing DNS, which is what most of my slides will be about today. A few words about public DNS and how that impacts centrality of recursive resolution. A few words about DNS as an attack vector, and then one quick slide on the update on the KSK rollover. So, in a traditional model of DNS resolution, it's the network operators, it's the service provider who runs recursive service. Whether you're the ISP, whether you're running a university network, or you're running an enterprise network, you as the operator are generally providing the recursive service. And when you're doing that, that works out well for you. You're able to meet a lot of goals. 2 big goals you're able to meet are regulatory compliance, when governments ask you to behave a certain way when users look up certain words, and of course, malware protection. DNS is a great place. Recursive resolvers are a good place to protect users from sites they shouldn't be going to. As you know, of course, over the last few years, more and more of your users, however, are not using you for recursive service. Instead, they're using public DNS, 8.8.8.8, 1.1.1.1, and so forth. There are many, many providers of public DNS and a couple of very popular ones. But the same sort of goals, the same sort of service paradigm works with public DNS. Because when you're a public DNS operator, governments can still serve you legal process. They can still tell you how to handle certain queries, and malware protection is actually some of the value add for some of these public DNS providers. Quad9, for example, tells you they're going to block access to certain sites that you don't want to be at. But these resolution models have some security concerns because DNS queries are sent in clear text. And if they're sent in clear text, anyone on the wire, anyone doing passive monitoring can see our query data. And then it's not just the query data, but there's also the metadata inside these queries that's also of interest. VPNs are a common solution that end users turn to for privacy and security, but it turns out that VPNs often don't include the recursive resolver we've chosen. And so the DNS data actually gets sent in unencrypted channels. And so it's this conversation between the user's device and the stub resolver and the recursive resolver, which is the most vulnerable to being censored or for queries and responses being rewritten. So the solution is fairly obvious, and that is, of course, to encrypt that channel. And in the last few years, the IETF has come up with 2 standards to do just that: DNS over TLS, DOT, and DNS over HTTPS, DOH, or DO. DNS over TLS, DOT is very simple, it's very elegant. It simply takes advantage of TLS that so many of our applications use today, and it leverages that to encrypt the DNS traffic between the stub and the recursive. And very nicely, it runs on its own port. Instead of UDP, port 53, it's running over TCP on 853. And as a service provider, that's good for you because you're able to very easily discover this DOT traffic. But this is the one we're really going to talk about today, and this is DOH. It's important to separate what the goal of DOH was by the protocol designers and what's happening. DOH as a protocol is fairly agnostic. It says, look, you as the user should get to choose who you trust the most to do your recursive resolution. In a simple example, all of us trust at least one bank. We've put our money there. And not only do we trust that bank to put our family's money there, we actually trust them enough to transact with them over the internet to do, digital banking. So if we trust a bank enough to give them our family's money and to transact with them over the internet, maybe the bank is the right company that should be doing our recursive service. DO runs on 443. and so does everything else in HTTPS. So the DOE queries are commingled with all of this web traffic and are not discoverable by you as a service provider. And that creates problems. As a service provider, DOE introduces a whole new range of challenges that you haven't previously had. You are no longer able to use your recursive service to meet your regulatory compliance and some filtering goals. And it turns out when an end user is at home and all of a sudden things stop working and they're using DOE, the first person they're going to call is you. Yeah, the DOE server went down, but they don't know what a DOE server is. And you don't know that they're using DOE necessarily. And it's certainly not your service, but you're the one they have a contractual relationship with, and you're the one they're calling. Meanwhile, this also blows out all of your parental controls, and it removes all of your ability to block access to sites that a court has ordered you to block. They changed their IP address behind the site, and your users are using DOE resolvers, which are off premises. The DOE resolvers don't know anything about the court order. Beyond just service provider concerns, there's some larger societal concerns as well. And one of those is about which laws apply when we're talking about DOE. In the traditional model, when you're providing recursive service, the recursive resolver your users are using is generally going to be in the same country as that user. And that makes all the legal stuff very easy. But when applications do their own DNS, and they're using DOE resolvers that can be found anywhere in the world, that's a whole different ball of legal jurisdiction. And that's really important when we think about complex topics such as content filtering and user data privacy regulations. And who gets to determine the resolver? The goal of the protocol when they wrote it was the user. The user decides who they trust. But it turns out that implementation details matter here. And what DOE does is it gives the application maker the ability to decide what resolver the application is going to use. So what happens when the application maker is dishonest? What happens when they purposely use a recursive resolver which steers queries away from the intended sites and instead sends them to sites that the application maker can profit off? And what if the application operator, what if the DOE resolver operator is monetizing the DNS data? And they're doing so without informing the end user and certainly without their consent. And the point is that bad and dishonest implementations can disempower end users. Instead of giving them the privacy and confidentiality assurances that DOT and DOH had a goal of, it actually can disempower them, and it does so in a context that users know basically nothing about, DNS resolution. So we have some difficult service provider concerns to talk about. We have some public policy concerns to talk about. And the question is, where do we talk about them? Well, we're here today. We can talk about them here. We need to talk about them at places like Center. The IETF is certainly talking about it. And if you'll beg my indulgence for just a moment, the IETF needs more operator input on this specific topic. And I know it's very difficult. Operators don't like dealing with the IETF, and I understand why. But here, there are only a couple operators involved in the discussion about applications doing DNS, but it's the operators who are, the biggest impact is on operators. So it's something, if you have some spare cycles, if you don't mind getting on some mailing lists, talking about applications doing DNS and some of the concerns you have as a service provider, it'd be really helpful to get involved. Right. So, applications doing their own DNS with DOE is new. But here's the thing. DNS was invented in 1983. It's 36 years later. And because DOH is being implemented by Firefox and by Chrome, 70% roughly of the world's browsers are going to have DOE turned on by October, by default. And most end users aren't going to know to turn it off. They're not even going to know what this option is if they happen to get that far in the settings. So what we're seeing is a gigantic shift in the DNS queries away from a traditional model that has worked for 36 years into this new paradigm which has its own challenges. And it's doing so very, very quickly. And in some cases, that's good, right? Because DNS privacy is a major concern. The regulators want more DNS privacy, generally speaking, and certainly end users want more privacy and more confidentiality about their data. So encrypting that data inside TLS or inside HTTPS, this is a good thing. But again, implementation details matter, and it's important to keep up with how applications are choosing to do their own DNS and how they implement DOE. So the good folks at APNIC recently conducted some measurements, and they wanted to look at centrality of recursive resolvers, how centralized recursive service has become. And so they asked a theoretical question: how many recursive resolver operators does it take to cover 50% of internet users? And their answer was about 8 or 9. And in their study, they found that Google public DNS 8.8.8.8 answered about 33% of the queries. There were also quite a few other big global resolvers, many of which were in China, like Resolver, China Mobile's Resolver, DNSPi is a big public resolver in China. Others that you know of, Comcast, the OpenDNS product, now called Cisco Umbrella. About 8 or 9 central resolvers covered 50% of the internet in their study. He's not in the room here, but I think, but he is here this week. Joe Abley, the CTO of PIR, the .org folks, recently released his interesting data that about 24 resolvers are responsible for about 80% of all traffic that org sees at their servers. And somewhere between 15 and 20% of all end user systems use Google public DNS, 8.8.8.8. So this kind of centrality is fairly new, and it's interesting because in some respects it's good. As a service provider, there are many service providers, especially smaller ones, that really like this because it's money back in their pocket. You don't have to spend the money and you don't have to spend the time building and maintaining large recursive resolver operator farms for your users because they're simply going to point everything to 8.8.8.8. But understand that the more folks who do that, the bigger percentage of the internet, the more internet users are subject to the control of a very, very small number of organizations. And when a very small number of organizations controls DNS resolution from the recursive side, they have a very outsized impact on what technologies get adopted. I put on the screen one example was DNSSEC. Well, Google public DNS is a very, very big supporter of DNSSEC, and they're responsible for just a very large amount of DNSSEC validation that happens today. If they choose not to support DNSSEC all of a sudden, and they have such a large percentage, up to 33% in one study, of the users, then that impacts technology. It also prompts concerns about content. What if one of these big public resolvers decides they want to filter some content? What if they're told they have to? Because they're all run by organizations. Google is run by an organization, and that organization is responsible in some way, shape, or form to a government. And if we look at history, we can see examples where Twitter and Facebook and some of these other popular media outlets today, they've tried to implement automated content filtering, and that really, arguably, didn't work out so well for them. But if you think about that, if you project that into the scale of DNS, wow, that's a lot of traffic, that's a lot of users. One more concern with centrality is, of course, preserving the IANN namespace. The internet tends to work pretty well when we're all operating in the same namespace. What happens if a public resolver operator decides, you know what, I'm going to start implementing my own TLDs? So one last word on centrality, which is, look, data privacy is a goal. And if it's a goal of efforts of like things like DOT and DOH, then perhaps it may be cause for concern or thinking about that a large percentage of query traffic is resolved by only the most popular recursive resolver operators. Because some of those resolver operators are homed in countries where there are either weak data privacy laws or there are laws that allow the home government to demand query data from the providers. Just a few quick slides about things happening with DNS as an attack vector. Last year, there was a fairly famous incident with myeitherwallet.com. Stop for a second. For about 10 years, about 11 years or so maybe, we've been talking about YouTube, right? Everyone here knows that Pakistan accidentally hijacked some of YouTube's traffic. And we've used that as the seminal argument for why BGP needs improvements. Well, to me, myeitherwallet.com is actually a really interesting event that brings all of this together, because it took a cryptocurrency wallet site provider, and the attackers were able to gain control of people's wallets. And how did they do this? Through route hijacking and through DNS. They simply, the myeitherwallet.com website was hosted on some servers which had authoritative name service in AWS. So the attackers hijacked the /24s where those authoritative name servers resided, and then they were able to stand up their own name servers on these IP addresses, which then gave out IP addresses to a fake myeitherwallet website. The user would get there, they wouldn't know they were at the wrong site, they'd put in their login credentials, it gets slurped right up, and seconds later, the real wallet has been emptied. And this happened because the provider didn't have BGP origin validation turned on. And this happened because the name servers, the zones, weren't being monitored frequently enough. So the attackers got really smart and really sophisticated. And now nation state actors can do military cyber offensive pre-positioning, somebody's term, for attackers gathering the intelligence that they need to launch military cyber attacks. The Cisco Talos folks created a pretty handy map, shows where these attacks are happening, and they're happening today. And it would take an hour to go through the attacks, but some of the interesting things that they were able to do here was keep attack durations very, very short, 10 minutes or less, to avoid detection. They did a lot of credential slurping, and one of the credentials they accidentally slurped were some credentials for something called EPP, which is how domain name registries and registrars talk to each other and exchange updates about domains and zones. And once they had those credentials, they were able to update authoritative name servers for important sites. And with that, they were able to get certificates, security certificates for TLS from places like Komodo and Let's Encrypt. You have that infrastructure compromised, you're then able to just do tremendous amount of data slurping, credential slurping, because once you have those credentials, you don't need the attack vectors anymore. One of the things they did that I thought was really interesting is they were able to compromise IMAP. But it's not they were compromising IMAP, it's that the IMAP servers were accessible to be authenticated from anywhere on the internet, not just from behind a trusted LAN. So if there were improvements that we see that we need that come out of all of these different attacks, if nothing else, it's about RPKI. It's about turning on BGP origin validation. And if you don't know how to do that, if you don't know how to turn on RPKI, at 4 o'clock, Ben Madison will be giving a tutorial on that, and I strongly encourage you to go. Again, about IMAP, you may want to consider making logging in only accessible from within a trusted LAN. For your important sites, for important things for your company and for your customers, strongly consider things like registry lock that disallow changes without out-of-band procedures. This was yet another example of the weakness of certificate authorities and why DNSSEC and DANE may be a better path towards security. All right, final slide. I work at ICANN, so I am obliged to talk about the KS-CRAE role, but it's only a single slide. We did roll the root zones key signing key in October of last year. It went fairly well, but if anything, it taught us that we don't know a whole lot about understanding the wide effects, what happens when we roll the root key. Generally, it worked well, but there was at least one major ISP in Ireland that was down for about 48 hours. Their DNS was down because they had the wrong key and they weren't getting updates. we're going to roll the key again. Don't know when. The IANN controls that. So the IANN is going to propose a strategy for public comment in the coming weeks. Some of the considerations there including are how often should we roll the root zones KSK. Oh, and by the way, at some point we really need to consider rolling the algorithm used to compute the key signatures. So those are the 4 topics of some of the things going on in the DNS operations world that I thought I'd share with you as network operators. I hope that was helpful. Thank you.